Welcome again. In the previous lesson, we had a learning on hypothesis testing. Let's take up a detail of hypothesis testing again in lesson 8. So, let's formally begin with what is hypothesis testing. A statistical hypothesis is an assumption about a population which may or may not be true. Hypothesis testing is a set of formal procedures used by statisticians to either accept or reject statistical hypotheses. As we did in lesson 7, we have statistical hypotheses are of two types: null hypothesis, which is represented by H naught, that represents a hypothesis of chance basis. And then we have alternative hypothesis, which is either represented by H1 or HA, and it represents a hypothesis of observations which are influenced by some non random cause. So, basically, to say that the null hypothesis is the hypothesis to be tested. The null hypothesis is sometimes referred to as the hypothesis of no difference, since it is a statement of agreement with conditions presumed to be true in the population of interest. In general, the null hypothesis is set up for the express purpose of being discredited. Consequently, the complement of the conclusion that the researcher is seeking to becomes the statement of the alternative hypothesis. The alternative hypothesis is a statement of what we'll believe is true if our sample data cause us to reject the null hypothesis. Usually, the alternative hypothesis and the research hypothesis is same, and in fact the two terms are used interchangeably. In this, a matter of point to be stated is that null hypothesis is not a universal statement. It is simply a quoted statement about a population which may or may not be true. So that means in hypothesis testing, we are not there to take up into consideration whether the stated hypothesis is true or false. All we are taking into consideration is that on the basis of sample statistics calculations, we need to predict or justify whether the given statement under the null hypothesis is accepted or rejected. So, for example, suppose we want to check whether a coin is fair and balanced or not. So, in this case, a null hypothesis might say that half flips will be of head and half will be of tails. That is, the coin is fair. Whereas the alternate hypothesis might say that the flips of head and tail may be different. So, in this example, the alternative hypothesis becomes that population proportion of flipping of heads and tails are equal. That is, capital P is zero point 0.5, whereas the alternative hypothesis is that the population proportion is not equal to zero point 0.5. For example, if we flip the coin 50 times, in which 40 heads and 10 tails came, then using this result, we need to reject the null hypothesis and would conclude based on the evidence that the coin was probably not fair and balanced. Data analysis used in business decision making often contains proportions to describe such aspects as market share, consumer makeup, quality defects, on time delivery rate, profitable stocks, and others. Business surveys often produce information expressed in proportion form, such as 0.5 of all businesses offer flexible hours to employees, or zero point 0.8 of all businesses have websites. Business researchers conduct hypothesis tests about such proportions to determine whether they have changed in some way or not. As an example, suppose a company held a 26% or 0.26 share of the market for several years. Due to a massive marketing effort and improved product quality, company officials believe that the market share has increased and want to prove it. So, this becomes a one tail hypothesis testing wherein null hypothesis is P is equal to 0.26 and alternative hypothesis is P is greater than 0.26. Other examples of hypothesis testing about a single population proportion might include a market researcher wants to determine whether the proportion of new car purchasers who are female has increased. Another example can be a financial researcher wants to test to determine whether the proportion of companies that were profitable last year in the average investment officer's portfolio is 0.60. A quality manager for a large manufacturing firm wants to test to determine whether the proportion of defective items in a batch is less than 0.04. So, all these are the examples of testing hypothesis about a proportion. So, suppose a manufacturer believes that exactly 8% of its products contain at least one minor flaw. The business researcher randomly selects a sample of 200 products, inspect each item for flaws, and determine that 33 items have at least one minor flaw. Now, suppose in this case, the company researcher wants to test the belief that whether the 8% of its products contain at least one minor flaw or not, then the null hypothesis and alternative hypothesis are P is equal to 0.08 and P is not equal to 0.08. If we want to test this hypothesis, then we can make use of Z test of a population proportion. We already took up Z test for mean in lesson 7. So the formula for Z test of population proportion is that Z is equal to, this is Z calculated, is equal to P hat minus P divided by square root of PQ by N, where P hat is the sample proportion, P is the population proportion, and Q is 1 minus P. So, if we want to find whether H naught is accepted or rejected as per the sample information, then we can take up this problem as follows. So, we are given that sample size consists of 200 of items and there are 33 items that have at least one minor flaw. So the sample proportion will be equal to 33 divided by 200. So this figure, that is 0.165, will be p hat, that is the sample proportion. Now we'll calculate z-score, that is z calculated, and z calculated as per formula will be p hat minus p, which is 0.08 in our case, divided by square root of pq by n, that is 0.08 into 1 minus 0.08 divided by n. N is 200. So we are getting z calculated as 4.43. Suppose this test is conducted at 5% level of significance. Then in that case, we'll have z tabulated will be equal to norm s inv 0.975. The reason why we are taking it as 0.975 is that since it is a two-tailed test and we have 5% as the level of significance, so two-tail means 2.5 from the right and 2.5 from the left. This we have already taken up in the previous lesson. So it will be norm SINV 0.975 and we will get 1.96. So our Z calculated is coming out to be greater than Z tabulated, and hence we say that our null hypothesis is rejected. So as per this case, we have that our sample evidence do not give enough information to support H0, or the belief of manufacturer is not abiding by as per the given sample information. With this example, let's proceed on to the formal process of hypothesis testing. In previous lesson, that is in lesson 7, we had determined that there are 10 steps to hypothesis testing. These 10 steps majorly coincides to these four attributes of hypothesis testing, wherein the first formal process for hypothesis testing states the hypothesis. This step involves stating both null and alternative hypothesis. The hypothesis should be stated in such a way that they are mutually exclusive. So, if one is true, then the other must be false. Then we go on with formulation of an analysis plan. The analysis plan is used to describe how the sample data is taken up to evaluate the null hypothesis. The evaluation process focuses around a single test statistic. For example, in the previous example, we focused on population proportion. Then analyze the sample data wherein we find the value of test statistic as per the analysis plan. So in the previous example, we actually found the value of test statistic, which is p hat, which was 33 divided by 200. And then we interpret the results, that is, apply the decisions stated in the analysis plan. So, if the plan of the test statistic is very unlikely, like it was in our test of proportion case, on the basis of null hypothesis, then we reject the null hypothesis. Now, when we are determining the hypothesis testing or when we are analyzing the hypothesis testing, then we have three important terms which forms the focus of our analysis, out of which margin of error and type 1 error are majorly considered, whereas type 2 error is used to determine the power of a test. In fact, 1 minus type 2 error, that is 1 minus beta, is used to determine the power of the test. So, the very first important factor is the margin of error. Margin of error M of interval estimation is defined as the value which is added or subtracted from the sample mean and that determines the length of the interval. So it's like that if we have calculated a statistic value from the sample, then as per the sample size and as per the level of significance that we are taking into account, how much error we are allowing from x bar to deviate with. And if this deviation is well within the confidence interval, then that is said to be the interval estimation of a particular statistic. Suppose we want to construct the interval estimate for mu. Then, in that case, using the margin of error and using the sample mean x bar, our lower confidence interval limit will be x bar minus z 1 minus alpha by 2 into sigma by root n, and upper confidence limit will be x bar plus z 1 minus alpha by 2 into sigma by root n. Now, to understand what is type 1 and type 2 error in hypothesis testing, let us take up a case study. Suppose a person is brought up in the court and the crime for which he has been produced in court is so heinous that the punishment for that is hanged till death. In this case, suppose the person was innocent but evidence showed that he is guilty. So, in this case, the judge might give up the punishment as hanged till death. However, this is a severe error as the innocent person is put to death. Such type of error in hypothesis testing is called as type 1 error because in this case our H naught would have been that the person is innocent. However, we are rejecting H naught on the basis of the evidences produced, which is not a correct decision. Similarly, we focus more on type 1 error while we are analyzing the hypothesis testing in statistical decision making. In this, if a guilty person would have been set free, then that is the type 2 error. So, in nutshell, type 1 error is rejecting the null hypothesis in favor of a false alternative hypothesis, and type 2 error is failing to reject a false null hypothesis in favor of a true alternative hypothesis. The probability of a type 1 error is typically known as alpha, while probability of type 2 error is known as beta. So this is the table which shows what is type 1 error and type 2 error. Failing to reject it's not when it is false is type 2 error, and reject it's not when it is true is type 1 error. Now we mainly focus on the level of significance while we compute or while we judge or while we analyze hypothesis testing. However, concept of beta is taken in terms of power of test. Power is the probability of rejecting the null hypothesis when in fact it is false. Power is the probability of making a correct decision when null hypothesis is false. Another way of defining power is it is the probability that a test of significance will pick up on an effect that is present. Then power is the probability that a test of significance will detect a deviation from the null hypothesis which should such a deviation exist. Power is also the probability of avoiding a type 2 error. So, simply to put up, power is the probability of not making a type 2 error. Bullard, who gave these multiple definitions of power, also states that there are four primary factors that affect the power. The very first is the level of significance. Second is sample size. Third is variability or variance in the measured response variable. And fourth is the magnitude of the effect of the variable. Majorly, one says that if we increase the sample size, then our test can be more powerful. But we state the hypothesis testing mainly on the basis of level of significance that we are taking into account. So with this, let's move on to the bifurcation of hypothesis testing. So hypothesis testing is mainly divided into parametric and non-parametric test. Now the difference between parametric and non-parametric test is parametric and non-parametric methodologies refer to those in which a set of data has a normal versus non-normal distribution respectively. Parametric tests make certain assumption about a data set, namely that the data is drawn from a population with a specific normal distribution most of the times, whereas non-parametric test makes fewer assumptions about the data set. The majority of elementary statistical methods are parametric, and parametric tests definitely have higher statistical power. So, wherever we have dataset available to us, we should try taking up the parametric tests. However, if the necessary assumptions cannot be made about a dataset, then non-parametric test can be used. Non-parametric tests as such do not require the data to follow normal distribution. These are also referred to as distribution-free tests and can provide benefits in certain situations where we are unable to apply the parametric tests. Majorly, when we have quantitative data, then we go with parametric tests. However, if we have some qualitative data, then we may switch over to non-parametric tests. So here's the table of parametric and non-parametric tests. Parametric tests can be z-test, pair t-test, normal t-test, t-test for two populations, Pearson correlation, one way ANOVA, whereas non-parametric tests are Wilcoxon-Ransom test, Mann-Whitney test, Spearman-Rank correlation test, Kruskal-Wallis test, Kormologov-Simrov test. Then there is chi-square test also, which is used as non-parametric test and which is majorly employed in business research. So let's go on to the reasons to use parametric and non-parametric tests. Parametric tests can be performed well with skewed non-normal distributions provided we have sample size to be greater than 30, because in that case, even if the distribution is non-normal, then the sampling distribution, because of CLT, that is central limit theorem, can be approximated to normal distribution. Parametric tests can perform well when the spread of each group is different. Parametric tests usually have more statistical power than non-parametric tests. Thus, we are more likely to detect a significant effect when only it exists in reality as per the sample information. Whereas non-parametric tests, they are used for the area of study which is better represented by the median, where we have a small sample size, and definitely where the data is of ordinal or ranked data, or there are outliers that cannot be removed from the data. And definitely where we have ordinal data, ranked data, or outliers that we can't remove from the data set. So depending on the availability of the data and the conditions stated, we can take up whether to go for parametric test or non-parametric test. Now, let's proceed on to the parametric test for testing of means. In previous lesson, we dealt with testing using Z statistic, and we even took up the case of single sample t-test. So, a single sample t-test or one sample t-test, as we did in previous lesson, is used to compare the mean of a single sample of scores to a known or hypothetical population mean when the population standard deviation is not given and sample size is less than 30. In this case, the requirement is that the data should be normally distributed. Scale of measurement should be interval or ratio, since T is a parametric test, and a randomized sample should be taken up from a defined population. One of the major conditions for conducting parametric test for single sample mean is that if population standard deviation is not known, then we can make use of t-test. Sample size small or large can be taken up as a second point. That is to say, even if our sample size exceeds 30, then also one may comply by the t-test, as when sample size exceeds 30 and sample standard deviation is known, whereas population standard deviation is not known, in that case Z and T will give approximately the same results. So the sample t-test or exact sampling theory can be extended to large sample theory, wherein large sample theory is supported by z-test. Basically, in this, we need to find whether the population mean is equal to the hypothesized mean or not. That is, there is no difference between the sample mean and the known or hypothesized population mean. The equation which is used for testing the hypothesis is T is equal to m minus mu divided by summation x square minus summation x square by n divided by n minus 1 upon n and taking the square root of it. So this formula can be modified to simply m minus mu upon s by root n. M is the sample mean. So if we are writing sample mean as x bar, so our t statistics become x bar minus mu divided by s by under root n, where s is the sample standard deviation. So let's take an example for this. This is an example from biomedical field, and in this we have that the researcher studied subjects with medical collateral ligament, that is MCL, and anterior cruciate ligament, that is ACL tears. Between February 1995 and December 1997, 17 consecutive patients with combined acute ACL and grade 3 MCL injuries were treated by the same physician at the research center. One of the variables of interest was the length of time in days between the occurrence of the injury and the first magnetic resonance imaging, that is MRI. The data is given in the table. So, in this, the researcher wishes to know if he can conclude that the number of days between injury and initial MRI is not 15 days in a population presumed to be represented by the sample data. So here we have the population standard deviation is not given and the sample size is less than 15. So we'll make use of t-test in order to find whether h naught is mu is equal to 15 or not. So we are entering the data. Now, since this is used for testing mean of single population, so we'll find first x bar or m, and that x bar is average of the days. Then we are given sample to be 17 in number, that is sample size is 17. And since we are making use of t distribution, so we'll go for degree of freedom, and degree of freedom is 1 less than the number of observations. Then we'll find sample standard deviation, which is nothing but STT EB. So this is the sample deviation. Sample standard deviation. Now let's take T calculated. T calculated will be x bar minus mu is 15 divided by s by root n. S by square root n. Now we are calculating. Now we are obtaining T calculated to be 0.8175. So let's assume level of significance to be 5%, and it's a two-tailed test. So T tabulated will be TINV 0.05. It automatically takes into account two-tail, and degree of freedom is 16. So taking the absolute value, we have T calculated is coming out to be 0.8175, and T tabulated is coming out to be 2.11 at 16 degree of freedom. So our calculated value in absolute manner is less than the tabulated value, and hence we say that on an average the number of days between injury and MRI is abiding by 15. So that is to say we are not rejecting H naught, wherein H naught was that the mean number of days between injury and MRI is 15 days. So, this was all about hypothesis testing, and with this, we end lesson 8. Wish you all a very, very happy learning. All the best.